So one thing, the first thing that is there is percentage dissociation idea, percent dissociation. The meaning of percent dissociation is obvious. So HA is going to become A minus plus H3O plus in a water solution, right?
Yeah.
So suppose you start off with A amount, then start off with this A amount, A molarity in this solution, then this happens A minus AX, right? X is a
Yeah.
fraction, right?
Yeah.
Yeah.
Like what proportion of A has dissociated,
Dissociated.
and this becomes AX and this becomes AX,
AX. Yeah.
and Ka for this acid will be A minus H3O plus by HA.
HA. Yeah.
So you will get Ka is equal to Ax
Yeah.
into Ax
A
by
square X
A
square.
into 1 minus x. So this becomes A into x square by 1 minus x,
Yeah.
right?
Yeah.
So if it is a weak acid, Ka will be small,
Small. Yeah.
A will be small, and it will be such that x will be less than 1, much smaller than 1,
Yeah.
right?
Yeah. Yeah.
Then you will be able to sort of ignore the 1 minus x and
One
call it
minus
1.
X. Yeah.
So you will write Ka will be equal to Ax square for a weak acid, and you will be able to get x from here. X will be equal to root over Ka by A.
Yeah. Yeah.
Now this x is technically a measure of how much what fraction of HA
Fraction.
molecules dissociated, right?
Yeah.
Acid dissociated by total, right?
Yeah.
Total initial present, right, is percentage dissociation into 100, right?
Yeah.
So this will be Ax is the dissociated part divided by total is A.
A. Yeah.
X is basically the measure of our percentage dissociation. For weak acids, this will be correct. So uh, if you look at the section for percentage dissociation, I think that is what they are telling you there. So percentage dissociation is defined as HA dissociated by HA initial, right?
Yeah.
Yeah.
And you can calculate that in normal situations. We just saw the way to do the calculation.
Yeah. Yeah.
So this is the, if your Ka is given and your initial concentration is given, you'll find X by this, right? This
Yeah.
part is clear, no, to everyone?
Yeah. Yeah.
Yeah.
Okay. Then the next thing is polyprotic acids. Polyprotic acids. So polyprotic acids are acids like say H2CO4 SO4 or H3PO4, right?
More than one.
So more than one dissociable hydrogen is there, right?
Hydrogen. Yeah.
So but it doesn't happen in one shot. Two hydrogens don't come out, right? What happens is this: H2SO4 gives H3O
H.
plus HSO4 minus,
HSO4. Yeah.
and there is
Yeah.
a Ka for this step, right? Ka1
The
from this,
K for the.
and then HSO4 minus itself could also dissolve and become H3O plus again, plus SO4 2 minus, and then there is a Ka2 for this step.
Yeah.
And this step goes 100% almost because it's a strong acid.
Yeah.
And this step will not go to 100%. This will be partial. Okay. So the way to calculate your eventual H plus concentration will be to take both these equilibria. So if you start with some A, you will get A minus AX here, right?
This 100% is only for H2SO4, right?
100% is only for the strong acids, not for every
Okay.
acid. H3PO4 will not be 100% even in first step.
Yeah.
So A minus AX will happen. So actually this will be 100%. So if you start with A, you get A here, right?
Yeah.
And A here.
Yeah.
And A here will go A minus AY, and this becomes A plus AY, right?
Yeah. Yeah. A plus A total.
Correct. And this is AY, right?
Yeah.
Yeah. Yeah.
So because it cannot be two different
Two
concentrations.
different H3. Yeah.
A has come from here and AY has come from here, right? So total is A plus AY. So you will write Ka2 will be equal to Ay into A plus Ay by A minus Ay, right? So A will cancel and it will be A into Y into 1 plus Y by 1 minus Y, right?
Yeah.
That will be the Ka2. Now, most cases Ka2 will be much weaker than Ka1.
K1.
And
Yeah.
because H3O plus was already present due to the first one, this reaction is further driven this side, right?
Yeah, yeah.
Because this is Le Chatelier's principle, the equilibrium will be driven towards the reactant side further because already the product is present, right?
Products is formed. Yeah.
The product that is supposed to be formed, this product, right? It's
Yeah.
already present
Yeah.
to a lot of extent, right? Till A, right? So
Yeah. Yeah.
in the absence of this H3O plus, the reaction would have gone to a certain level, right? But if H3O plus is already present, then the reaction will go to a lesser extent, no?
Yeah. Yeah.
You understand? It is balancing the stress that has been caused.
Yeah. Yeah.
So actually, Y will be lesser than what it would have been if it was just this, right?
Yeah. Yeah.
If it was just this reaction happening, you have brought a solution of this, then it would have been this 2 minus plus H plus, right?
Yeah.
And you would have gotten A minus AY, 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 right? This would have given you a value of Y, right? A square, Y square, so A cancels, AY square by 1 minus Y, right?
Yeah.
This would have given you some value of Y, but the value of Y here will be lesser than that, right?
Yeah. Yeah.
Because this is already present, right?
Yeah. Yeah.
Yeah.
So you can definitely ignore this.
Yeah. Yeah.
Like it will be even lesser than normal. Okay. So you can definitely 1 minus Y and 1 plus Y will be 1 and 1.
Yeah.
Okay.
Got it.
So you'll get Y is equal to simply Ka2 by Y by A.
Yeah. Yeah.
Right? So you will get the amount of dissociation here. So you'll get final concentration of H3O plus, right?
Yeah.
Yeah.
Correct. In case the first reaction was not 100%, then you have to do Ka1 part also, right? Like for
Yeah.
H3PO4, I will do Ka1 separately, right? H3,
Yeah. Yeah.
I will do H plus plus H2PO4 minus, and then I will do H2PO4 gives HPO4 2 minus plus H plus, and then I will give HPO4 2 minus will give PO4 3 minus plus H plus, right?
Yeah.
Now
Yeah.
this is Ka1, this is Ka2, this is Ka3, and progressively the acid becomes weaker,
Weaker. Yeah.
right? The
Yeah.
acid
Yeah.
strength becomes weaker and weaker progressively, because obviously taking a hydrogen out from a negatively charged thing will be more difficult, no? Taking a proton out.
Yeah. Yeah.
And from a two negative thing, it will be much more difficult, right? So the acid should become weaker, right?
Yeah. Yeah.
So now if you start with A here, let's do A minus AX here and AX here and AX here, right?
Yeah.
And AX here, and let's say Y fraction of it gets reacted, right? Right? So AXY should be produced, right?
Yeah.
Yeah.
But it is already AX, so
AX
plus AXY,
Yeah.
right? And this is AXY, right? Correct.
Yeah.
This is also AX plus
AX.
AXY.
Yeah.
And AX plus AXY is here, right? AXY is minus something, right?
Yeah.
AXY
Minus
minus AXY
Z.
into Z, let's say. So this is AXYZ, and this is AX plus AXY plus
AXYZ.
plus AXYZ. So I'll put this everywhere also, plus AXYZ, right? Correct.
Yeah.
Now these are the concentrations of everything in the solution, right?
Yeah.
At equilibrium. So it will all satisfy these equations, right? Ka1, Ka2, right?
Yeah. Yeah.
My equations will be Ka1 will be this into this by this, right? Ka2 will be this into this by this, right?
Yeah.
Yeah. Yeah.
A3 will be this, right?
Yeah.
You realize that because of the H plus being produced by the first one, the second and the third reactions are further suppressed,
Further suppressed. Yeah.
right? Because already H plus is present, right?
Yeah, yeah.
Yeah.
And there will be a huge difference between the Ka1 and the Ka2 and Ka3 values, right?
Yeah.
You'll be able to make many simplifying assumptions here. So most of the time you will be able to ignore, say, Ax, Y, Z with respect to Ax or something, right?
Yeah.
It will become simple when you look at the actual values and do the
Yeah.
So right now it might look complicated, but I have done it using variables just so that you can understand how to split it,
Yeah.
right? So whatever is produced, that itself will again dissociate to a certain value, right? To a certain fraction.
Yeah. Yeah.
That fraction is the Y, right? And
Yeah.
this fraction is the X, and this the Z fraction, right? So polyprotic acids, he is describing the same thing. And now for H2CO3, he has done the calculation and shown you, right? So look at the steps for H2CO3 once. He is giving you the values of Ka1 and Ka2, okay? And H2CO3 carbonic acid, the values for Ka1 are 4.3 into 10 power minus 7, and Ka2 is 5.6 into 10 power minus 11, right?
Yeah.
So a
Yeah.
10,000 order difference here, right?
Yeah.
So now see, he started off with some 0.02 molar of H2CO3, did a minus X plus X plus X, right?
Yeah.
So this is the first equation. Then HCO3 is available for X concentration, right?
Yeah.
He is doing a simplifying assumption. He's saying that the principal reaction is the first reaction, and that is going to decide the H3O plus concentration, right?
Yeah. Yeah.
I mean, we can do a one
Mainly.
step further. He is immediately doing the approximation, okay?
Yeah.
So we can do one step further and say HCO3 X amount will dissociate to a Y degree, right? So you'll get X minus XY will be equal to the H3O plus will be X plus XY,
Yeah.
and CO3 2 minus will be XY, right?
XY. Yeah.
Yeah.
Correct. And from the Ka2 values, you can find the XY and all, right?
Yeah. Yeah.
And from this equation, the way he has done it, he is doing X square by 0.02 minus X is equal to my Ka1, right?
Yeah.
And 0.02 minus X, he is almost calling it 0.02 only because that will be small. Because the first
Yeah.
one,
Yeah.
first K is also small. See, first
Yeah.
K
Yeah.
is also 10 power minus 7, right?
Yeah.
So he gets the value of X as approximately 9.3 to 10 power minus 5, right? And he's saying, see, approximation is justified because this is too small as compared to 0.02.
Yeah.
Right?
Yeah.
So the big concentrations by that he means the concentrations from the principal reaction, right?
Yeah. Yeah.
Are X is equal to H3O plus is equal to HCO3 minus is equal to this much, and H2CO3 left over is almost same as what was initial, right?
Yeah.
Like nothing has been dissociated.
Dissociated.
So the small concentrations obtained from the are obtained from the subsidiary equilibria, right? Of
Yeah.
HCO3.
Yeah.
So now see, the X amount that was there for HCO3 minus, that will dissociate to a certain degree, right? Correct.
Yeah. Correct.
And he has used that to calculate the CO3 2 minus concentration, the CXY that we are talking about, right?
Yeah. Yeah.
Correct.
Yeah.
That is much smaller also. That is much more small. And once you know the H plus concentration, which is X plus XY, and XY can be ignored and compared to X, right?
Yeah. Yeah.
X is 9.3 into 10 power minus 5, and XY is quite small, no?
Yeah. Correct.
Correct. So you can sort of ignore that. So once you know the H plus concentration, because it is a water solution, you know OH minus concentration.
Yeah.
Yeah. Yeah.
H plus into OH minus should be 10 power minus 14. So OH minus is coming as 10 power minus
10 power minus 10. Yeah.
Correct. So
Yeah.
is the solution acidic or basic? Solution is acidic or basic is decided by the
Temperature. Yeah.
no, by the comparison between H plus and OH minus, no?
Yeah. Yeah.
I mean, acidic and basic will be decided about by which one is bigger, H plus or OH minus.
Yeah. Yeah.
Yes. Yeah.
So H plus is higher than OH minus, so solution is acidic, right?
Acidic. Okay.
Hmm.
pH of the solution will be something less than 5 because 5 minus log 9.3, right? So
Yeah.
almost 4
Yeah.
and all, right?
Yeah.
Correct.
Yeah.
So that is the method. Now he has done another example. You can check it out. Sulfuric acid example, right?
Yeah. Yeah.
Bases, weak bases. This is section 12. This is also exact same thing. There is nothing different here. It's just that the first reactions, the possible reactions are something accepting a proton, right?
Yeah.
Hmm.
Yeah.
Right? That is the only difference. And a base will accept a proton from water, right?
Yeah.
And it will become CO. Suppose you look at example 14.13, right?
Yeah.
That is codeine, a drug used in a painkiller, is naturally occurring amine that has a Kb value of 1.6 into 10 power minus 6, right? So let's say we do this 14.13. So codeine is an amine which has a Kb value of 1.6 into 10 power
1.6 into
minus 6.
6. Yeah.
Okay, and now you have to calculate pH and concentration of all the species that are present in a pH and concentration of all species present in a solution of 0.0012 molar codeine, right?
Yeah.
Yeah.
So, okay, so there is a solution of codeine. So now the things that are present are codeine, which is an amine or a base. There is water, which can act as an acid or a base.
Yeah. Yeah.
Water can act as a base also, right?
Yeah.
Hmm.
So now, obviously, this is a base, right?
Yeah.
Two bases and one acid.
One acid. Yeah.
Yeah. Yeah.
So the two possible reactions are water acting with codeine, where this is the base and this is the acid,
Yeah.
and this gives codeine H plus OH minus. This is one reaction. This is the reaction for which the Kb has been given to you, right?
Yeah. Yeah.
Yeah.
The other possible reaction is water acting like an
Water
acid to water,
with
right?
water. Yeah.
Water with water, right? And
Hmm.
that will give, that is the opposite of the, that is the normal Kw reaction,
KW.
right? And the
Yeah.
Kw
Yeah.
is 10 power minus 14, right?
Yeah.
Hmm.
Now, which is more powerful? K, right? This is
Yeah.
1.6 into 10 power minus 6, right?
Yeah.
Hmm.
So the
Same.
comparison between these two reactions, this reaction is the principal reaction,
Yeah. Principle.
Yeah. Yeah.
right? So this reaction is principal reaction, so we'll sort of not worry about this right now.
Yeah.
Okay, and we'll think of this reaction, right? So now we have 0.0012 present, right? And at initial condition, and then you do a minus 0.0012x, right? Correct.
Yeah.
Yeah.
And this should be 0.0012x, 0.0012x, right?
Yeah. Yeah.
Yeah.
So your final Kb should be equal to 0.0012x square by 1 minus x, right? After doing
Yeah.
the calculation,
Yeah. Yeah.
cancel one thing. It's the same thing that happens for weak acid, right?
Yeah. Correct.
Just that the reaction is a little different because it's a base, right? And it's a Kb.
Yeah.
So now I will say that since this looks like a small enough value, 1 minus x will be close to 1, and therefore x will be Kb by 0.0012 root of that, right?
Yeah.
Yeah. Yeah.
1.6 into 10 power minus 6 by this is 12 into 10 power minus 4, right?
Yeah.
12 into 10 power minus 4 and root of that. So
Root
this
of.
becomes 10 power minus 2 and 1.6 by 12, right? So 16 by 12 into 1 by 10 into 10 power minus 2, right?
Yeah.
So 16, this becomes 4 by 2 root 3 and 10 power minus 1. Okay, that is annoying. 10 power minus 1 by root 10 also, right?
Yeah.
Right. So this is 2 by root 3 into root 10, right?
Yeah.
Root 10 is 3.162. So 2 by 3.162 into 1.732 into 10 power minus 1, right?
Okay.
That is my x, right? And
Yeah.
3.1 into 1.7. So do an approximate calculations. 3.2 into 1.7, let's do. Okay, so this becomes 32 into 10, 320, 7, 210, 224. So 544,
Yeah.
right?
Yeah, yeah.
5.44,
Yeah.
right? 2 by
5.4.
5.44 into 10 per 2 by 5.44. So 2 by 5.5, let's say 20 by 55, right? So 4 by 11.3, 0.37, 0.36, 0.36 into 10 power minus 1, right?
Hmm.
0.036, right?
Hmm.
Yeah.
0.036, however, cannot be ignored with respect to this, I think, right?
Yeah.
1 second, let's think. 0.036 can be ignored with respect to 1. No, it can't. You should not ignore this, okay?
Okay.
Because this is quite substantial, no? It will become 0.97 and all,
Yeah. Yeah.
right? So actually now it is a
Yeah,
annoying
yeah.
question because it's a quadratic now.
Yeah. Yeah.
Now it will be slightly annoying. So
Yeah.
he is ignoring it, however. He has done the root of 4. Okay, our calculation is only wrong.
Calculations are, yeah. He
Uh,
got 4.4 into 10 to the minus 5.
Kp is this, so minus x. What have we done wrong? 1 second. 0.0012 minus x plus x plus x. So 0.00. Oh, he has done plus x square by this, right? We did by percentage dissociation. That
Yeah,
method we did.
Yeah.
We
yeah,
could have
yeah.
done a total thing, like a total amount that got reacted, right?
Yeah.
That will be slightly more convenient to calculate. Like it's the same thing, it's just that our calculation has gone wrong. So,
Yeah,
Yeah.
so
yeah.
he has done x square by 0.0012 minus x, and that becomes almost 4.4 into 10 power minus 5, where he's ignoring it with respect to 0.0012, right?
Yeah. So if we do
Hmm.
0.0012 minus x is 0.0012.
So basically his value was
Same.
what? 0.00004, right?
Yeah.
He is ignoring 4 zeros and 1 4 after that.
Okay. So first he's saying that x is like negligible. And then,
No, he is not saying that. He's saying since his k expression was coming as x square by 0.0012 minus x, right?
yeah.
This was the expression, and once the assumption that he's making is 0.0012 minus x is same as 0.0012,
Yeah.
right?
Yeah.
The value of x that came
Yeah,
out was 4.4 into 10 power minus 5, right?
Yeah.
And this value is what? 0.000044, right?
Yeah.
Now
Yeah.
you can ignore it because 4 significant digits, there is no change, right?
In case the answer was not that, we could not have like
If
something bigger.
this subtraction was not ignorable, see, 4 significant digits is 00 only, no?
Yeah.
After that, you
Also a
don't know what
zero.
it is. So it is
Yeah.
almost going to be 0.0012 only,
Yeah.
right?
okay. Yeah, yeah.
I mean, you understand what I'm saying?
Yeah. Yeah.
If you had
Yeah,
more till the significant digits where you know the answer, it was 0, right?
Yeah.
After that, there was some stuff, but anyway, you don't know what this is, right?
Yeah.
yeah, yeah.
So you can ignore it. So then his assumption is correct, and his assumption is correct, and he knows the x value, right?
Yeah.
And his x was the total value of OH minus and all. It was not like we made a mistake by taking it like a percentage dissociation type of situation, right? We did
Yeah.
like this. We should have
Yeah.
taken the whole
Yeah.
thing as x. Okay,
X only. Yeah.
that would be more convenient. Okay, so that is fine. So x comes and x
Yeah, yeah.
comes and everything comes, right?
Yeah.
All the concentrations will come. X is also the OH minus concentration. So from OH minus concentration, you will be able to find H plus concentration, which will be 10 power minus 14 by 4.4 into 10 power minus 5, right?
Yeah.
So notice that it will be of the order of 10 power minus 9, right?
Yeah. -9.
And
Yeah,
therefore the solution is basic. Solution is basic because this is much less than OH minus.
OH minus. Yeah.
Okay.
yeah, yeah.
So this one is weak basis, relation between Ka and Kb. So now he will show that Ka into Kb is equal to Kw for any conjugate acid base pair. So how will he show that? He will take the example of this weak base ammonia. Okay.
Yeah.
So one reaction that he writes is ammonia with water will give NH4 plus OH minus, right?
Yeah.
And the other reaction is NH4 plus acting like an acid with water will give NH3 plus H2O, right?
Yeah. Yeah.
Right. So so basically what he's saying is for a conjugate base and acid pair, right?
Yeah.
One reaction becomes NH3 plus H2O becomes NH4 this is the acid here and this is the base.
NH4.
So NH4 plus OH minus,
OH
right?
minus. Yeah.
This is the Kb value, right? And the other reaction is when NH4 plus acting like an acid with water acting like a base.
Base.
So this will be NH3 plus H3O plus, right?
H3O plus. Yeah.
Correct. This is the Ka, right?
Yeah.
This is NH3 acting like a base. This acting like an acid, right?
Yeah.
So now it is obvious that these are reverse of each other, right?
Yeah.
If you add up all of them, right, you'll cancel all the NH3 and all, right?
Yeah.
And what you will get is H2O plus H2O gives
H3O
plus OH minus, right?
Yeah.
So definitely after addition, this reaction becomes the Kw, right?
Kw. Yeah.
And when you add two equations, you have to multiply the Ka values, right?
Yeah.
Why? Because you can prove it by actually writing the expressions. Kb is equal to simply NH4 plus OH minus divided by NH3, and Ka is NH3 H3O plus divided by NH4 plus.
Yeah.
And when you multiply, you get cancelled everything and it becomes H3O plus OH minus by nothing.
That's
right? This is the Kw, right?
Yeah.
So he has proved that Ka into Kb is equal to Kw for any conjugate acid base pair. Right?
Yeah.
Okay, then he is saying what we have shown in this particular case is true in general. Whenever chemical equations for two or more reactions are added to give the equation for a net reaction, the equilibrium constant for the net reaction is the product of the equilibrium constants of the individual reactions.
Yeah.
So that is going to be useful for you because sometimes you might know Ka, but you need a Kb value.
Kb, yeah.
And not any arbitrary Kb you will get, but you will only get the Kb for the conjugate thing. Right?
Yeah.
So that is going to be useful. So that he has explained. Acid base properties of salts. So salts basically can be formed from multiple situations. There are cases like strong acid, strong base, in which case the solution will become neutral. Then there is a case for strong acid, weak base, and weak acid, strong base, when the solutions will be dominated by the strong acid. Like it will be acidic solution for strong acid, weak base. And it will be basic solution for weak acid, strong base.
Yeah.
Okay, so he's explaining. So salts that yield neutral solutions. So salts such as NaCl that are derived from strong base and strong acid yield neutral solutions because neither the cation nor the anion reacts appreciably with water to produce H3O plus or OH minus. Why? Because it was a strong acid only because it could dissociate and that cation was stable and all. No? That anion was stable. So HCl, why was it a strong acid? Because it could easily give H plus and Cl minus, and Cl minus is fine existing on its own. Cl minus was quite stable because it had a filled outlet. That's why it was dissociating so nicely. Right? Similarly, NaOH, Na plus and OH minus it was becoming, and Na plus was stable, right? That's why it was dissociating easily, right? So if you have a salt of Na plus and Cl minus, right? So in a solution, Na plus and Cl minus can nicely exist. There is no issue with them. because they will be hydrated by water molecules surrounding them, and after that they will be stable. Like
Yeah.
there is no further reaction that they will have. You understand?
Yeah.
Because they are on their own, they are stable. So further they will not react much with water. Therefore, the solution will remain neutral and it will not be acidic or basic.
Yeah.
Right?
Yeah.
Because after that, they don't have any tendency to do much. They already are stable. Right?
Yeah.
Salts that yield acidic solutions. So now look at a salt like NH4cl, right?
Yeah.
So Cl minus is not going to do much, right? But NH4 plus, right? NH4 plus has a tendency to behave like an acid.
Yeah.
Okay.
Yeah.
NH4 plus is going to behave like an acid and weak base and strong acid. So the whole solution will become acidic, no?
Yeah.
Right?
Yeah.
So
Yeah.
notice here that NH4 plus will react with water to give NH3 plus or H3O plus, right?
Yeah.
That was because it was coming from, it was a conjugate of a weak base.
Weak base.
So it was a strong enough acid on its own. What I'm saying is basically, if your Ka Kb product is Kw, right?
Yeah.
And if
Yeah.
your Ka side is
K
weak,
is
then
small,
Kb is
yeah.
large, right?
Mm.
So if you have a weak acid, let's say, so Ka is weak, right? Then Kb
Yeah.
will be small for the large for that.
Yeah. Yeah.
So when a weak acid will give a, when you have a conjugate base of a weak acid, that base will be quite strong.
Yeah.
Right?
Yeah. Yeah.
Similarly here, when you have NH4 plus, right? That was the conjugate acid of a weak base called ammonia.
Yeah. Yeah.
A
Yeah.
weak base ammonia, and the conjugate acid of a weak base will be strong, fairly strong, right?
Yeah.
So this makes the solution acidic.
Okay.
This
Yeah.
makes the solution
Yeah.
acidic for NH4cl. Now, why is NH4cl not basic? Because of Cl minus? Because HCl was a very strong acid, right?
Yeah.
Very
Yeah.
strong acid. So Cl minus is a very weak base.
Yeah. Yeah.
Cl minus has no tendency to accept protons or anything. Very weak
Yeah.
base.
It can't.
As compared to NH4 plus, which was a fairly strong acid.
Strong
Right?
acid.
Yeah. Yeah.
So the overall
Yeah.
solution turns to be acidic, right? NH4cl, right?
Yeah.
Are you
Yeah.
understanding what he's saying?
Yeah.
Yeah.
So similarly, you can discuss the case when it is a strong acid, weak base also. Strong acid, weak base solution we have already seen. Strong base, weak acid, right?
Yeah.
So for
Yeah.
example, CH3COO salt,
So.
sodium acetate, right? So
Yeah.
the base was NaOH, the acid was CH3COOH.
Yeah.
Yeah. Yeah.
So now this Na plus has no tendency to have any acidic behavior.
Acidic. Yeah.
Not much acidic, right?
Yeah.
Acidic tendencies here. While on the other hand, this is a weak acid, so its conjugate base has a quite strong tendency to
Strong.
act like a base.
Base. Yeah.
Fairly strong base. Because the acid itself was weak. Right?
Yeah.
Yeah.
The solution will be dominated by this behavior, which is a fairly strong base. This doesn't matter, right? So the solution will become basic, right?
Yeah. Yeah.
So what will happen in the solution? The acetate ions will react with water and will behave like a base. So will accept a proton from water and will become this plus OH minus, right? This is what happens when you mix sodium acetate in water, right? Na plus doesn't do much. Na plus just gets hydrated and surrounded by H2O, H2O, H2O. Stays like this.
Yeah. Yeah.
Right? It stays like this. It is stable enough like this.
Yeah.
Correct? So this is what happens. Are you understanding?
Yeah. Yeah.
Okay. So this is this section. You can read up whatever is the list. So example 14.15, for example, calculate the pH of an acidic salt solution, right? So he has given an example of AlCl3, right?
Yeah.
0.1 molar AlCl3, he has said, and he has given Ka of acidic, Ka of the aluminium H2O6 3+, right, is given, right?
Yeah.
So when you dissolve this, what will you get? Okay, let's just discuss this once. So AlCl3 is there, and 0.1 molar solution. Okay. And what information is given? Ka for Al H2O6 3+ is 1.4 into 10 power minus 5, right?
Yeah.
Okay. So when you dissolve this, what happens? It becomes Al3 plus 3Cl minus, right? This Cl minus will remain inert
Yeah.
because it is a strong bases conjugate acid, strong acids conjugate base, right?
Base,
Yeah.
This is going to remain inert. However, this, right? This is going to be fairly acidic. No, see,
Yeah.
this acidity for this. What was it coming from? It was coming from some AlOH, right?
Oil,
Thrice.
yeah.
AlOH thrice, this base. This base has given you this cation, right?
Yeah.
Correct? This base is a weak base.
So strong
Yeah.
acid.
Yeah. Strong
So
acid.
this one will become a fairly strong acid, and the value for this is given. Why has he written this structure? Because it will be hydrated, it will not be alone.
Yeah.
Right? So Al H2O6 3+, right, will act like an acid, and plus water will give H3O plus something. It will lose a proton from somewhere. Right?
Yeah.
Actually, you can write it Al
Like
H2O5
5 times and then
OH, and it becomes 2+.
Yeah.
Right? One of the
Yeah.
waters will lose,
Yeah.
right, a proton. And I don't care about what this structure is. I only care about this, right? So the Ka for this is given. Ka for this is given. That is equal to 1.4 into 10 power minus 5 is equal to basically H plus whatever this structure is divided by AlH2O6 concentration, right?
Yeah.
AlH2O6 3+ concentration, right? So
Yeah.
initial was
Yeah.
0.1, and let's say 0.1 minus X happens, 0.1 minus X, and this is X and this is X, right?
Yeah.
So this becomes on top X squared by 0.1 minus X, right? And I will sort of ignore it first and see if it is fine, right? So 1.4 into 10 power minus 6 and root of that, and root of 1.4 will be some 1.14, 140, around 1.13 square, no, 12 square, 1.2, 1.2 into 10 power minus 3, right? That will be the approximate value of X. Now clearly X can be ignored as compared to 0.1.
Yeah.
Right? So that is a correct calculation then. So X will be this much. So now pH is going to be 3 minus log almost 2.9, right? 3 minus log 1.2, right? pH.
Yeah.
Right. So we have found the pH of this solution, right? And it is clearly acidic. See, this is H plus concentration, right?
Yeah.
OH minus will be 10 power minus 11 or something nearby.
Yeah.
It is an acidic solution. And let's check, he is getting 2.92. Okay. So same thing. Are you understanding?
Yeah.
Okay. Then 14.15, factors that affect acid strength and basic strength. Factors that affect acid strength. So let's see. So there are many factors actually. He's saying, although a complete analysis of the factors that determine the strength of an acid is complex, he will discuss some bits of it. So the extent of dissociation of an acid HA is often determined by the strength and polarity of the HA bond, right?
Yeah.
The weaker the HA bond, the easier it is to break it, right?
Yeah, yeah,
and the
Yeah.
stronger the acid it will be, right?
yeah, yeah.
So strength of Ha bond, as we saw in section 8.10, is the enthalpy required to dissociate Ha into an H atom and an A atom, right?
Yeah.
The polarity of the Ha bond increases with an increase in the electronegativity of the A and is related to the ease of electron transfer from H atom to A to F. See. So if you have more electronegative A, right,
Yeah,
then it will
Yeah.
draw the electrons more towards itself and the
yeah,
bond will be
yeah.
polar, right?
Broken, yeah.
Yeah. Yeah.
So the more polar the bond, the easier it will be to separate the H plus, right?
Yeah,
Hmm.
Right. So to lose an H plus, it will be easier if it is a polar bond and already it had a partial positive, right?
yeah, yeah,
If it was non-polar, then you have to separate the entire electron density and do it.
yeah, yeah.
However, if it is already polar, it is already half of the way it has already gone.
Yeah.
Hmm.
So therefore, when you compare HCl, HBr, HI and all, right,
Yeah, yeah.
the more stronger polarities will lead to stronger acid,
Stronger acids. Yeah.
right? So
Yeah.
the variation in polarity in this series is, however, much less important than the variation in bond strength. Now, obviously, there are two factors here. One is polarity, one is bond strength, right?
Hmm.
Now, bond strength doesn't have to follow the same order as electronegativity, right?
Yeah, yeah.
So bond strength also matters, and that matters more than the polarity difference. Okay, so he's saying variation in bond strength is more important, and bond strength variation is slightly anomalous for HF. HF is not a very strong bond because the particles, the atoms are really tiny and they are quite close. So nuclear repulsion is quite high.
Yeah, yeah.
HF
Okay.
HF is very small, so there is more nuclear repulsion and the bond is not as strong as you would have expected. On the other hand, HCl is quite a strong bond, and after that, bond strength will decrease.
Yeah.
See, normally what should have happened is bond strength should have followed this order. HF should have been a stronger bond than HCl, HBr, HI.
Yeah, yeah.
Why? Because as you go bigger and bigger, right?
Yeah.
As you go bigger and bigger, the distance between this charge cloud and this nucleus, right,
Yeah.
becomes
Yeah.
larger and larger, right?
Yeah. Yeah.
Larger and larger, this distance, right? Correct?
Yeah.
Yeah.
So obviously these are opposing factors. There are two factors here, right? One
Yeah.
is repulsion, nuclear repulsion also,
Yeah, yeah.
and one is attraction of the charge cloud to the nuclei also, right?
Yeah. Yeah.
So it is complicated and it's not predictable. It's just that you have done experiments and figured out that the order is this: bond strength are higher. This is bond strength, HI, and HF is less than HCl. Okay.
Yeah.
So HF is weaker than HCl, but HCl is stronger than HBr and HI. So
Yeah.
because here everything is perfect in the sense that electrons are attracted to the nucleus also fairly strongly, and there's not so much repulsion also like here. And here there is not so much repulsion, but attraction is also weak, right?
Yeah.
Yeah.
And attraction is also weaker here,
Yeah.
right? So the
Yeah.
bonds are not so strong,
Yeah.
correct? So in general, so he's saying in general, bond strength decreases with increasing size of element A down a group, right?
Yeah.
In general, bond strength decreases. So strongest bond will be HCl as compared
Yeah.
to HBr and HI,
Yeah.
right?
Yeah.
For HA, where A is FCl, Br or I, the size of A increases from F to I. So bond strength decreases and acidity increases from HF to
Yeah.
HI, right?
Yeah.
Because
Yeah.
bond strength will be smaller, no, for HI.
Yeah.
Yes. Yeah.
Hydrofluoric acid is a weak acid, whereas HCl, HBr, HI are strong acids.
Strong acids. Yeah.
Right? So HCl, HBr, HI are strong acids because bond strength is decreasing, right?
Yeah.
Yeah.
Okay, so he's saying bond strength for HA is strong, HF is stronger. Yeah, let's see this.
Oh,
HF bond strength. Oh, okay. So I was slightly wrong. HF bond strength is also stronger. So it is following
Okay.
a common trend.
okay.
Hmm.
Okay. So there is no mistake in the trend then, right? See, on the next page, he has written the values of kilojoule per mole bond strength, right?
Yeah, yeah.
570, 432, 366, and 298, right?
Yeah.
Yeah.
So there is no confusion here, then there is no problem.
Yeah.
Okay. It is following a standard pattern, right?
Yeah.
As you become bigger and bigger, the bond strength is weaker.
Decreasing. Yeah.
So
Yeah.
acidity is increasing,
Increasing.
right? So then binary acids, for binary acids, okay, so he did not even bother about the polarity, right? So
Yeah.
polarity was HF was highest, so it should be strong, and this is lower, this is lower, this is lowest, right?
Yeah.
The electronegativity difference I'm talking
Yeah. Yeah.
right? So according to that, you should have HF is the strongest
Except for
acid,
strongest acid. Yeah.
but the factor of bond strength is much more important than the factor of polarity.
Okay. Yeah.
So
Yeah.
that determines the overall trend rather than the bond strength.
Yeah.
Yeah.
Okay. Okay. So we have this thing. Then for binary acids, now where the structure is almost similar, like carbon, methane, ammonia, water, and HF, right? So in each of these, you have one atom in the second period, and that is reacting with hydrogen to form a compound, right?
Yeah.
Yeah.
So here, the only difference is that the atom has different polarities, right?
Yeah. Yeah.
Atoms are becoming increasingly more electronegative as you go to the right.
Yeah. Correct.
So here, it is following the normal electronegativity trend, where
HF.
you have HF should be strongest acid
Strongest
out of all
acid.
of these,
Yeah.
right?
Yeah.
Yeah.
So far he has talked about two things. He has talked about electronegativity. He has talked about bond strength, right?
Yeah.
So both the factors could operate, and they may be in opposition to each other or whatever, right? And in one case, he has talked about the fact that bond strength is much more important, and therefore HF, HCl, HBr, HI acidity will be highest for HF
Yes.
as you go
Yeah.
down the group. However, in this comparison, where you have CH4, NH3, H2O, and HF, you have bond strengths are fairly similar, and electronegativity is varying. Okay, electronegativity is varying, and electronegativity is increasing as you go right. So strength of the acid is increasing.
Yeah. Yeah.
Okay. Yeah.
Here, all the bonds are fairly strong. It's not like the bonds can easily break because their second period atom sizes are not very different.
Yeah.
Yeah.
Understand? Carbon, nitrogen, oxygen, fluorine, atom sizes are not very different.
Not different.
Slight difference, but obviously not like HCl, Br, I, and fluorine, right?
Yeah. Yeah.
That is a huge difference in atom sizes, right? So as you go down a group, you'll have huge difference in atom sizes, so huge difference in bond strengths.
Yeah.
Yeah.
If you are in the same period, the size will not be so different, so bond strength will not be so different.
Yeah. Yeah. Correct.
Right? And therefore, polarity is the factor that dominates.
Yeah. Yeah.
Are you understanding?
Yeah.
Yeah.
So here, this is the reason for this trend. Then let's look at it. What other factors has he mentioned? So for example, oxo acids, H2CO3, HNO3, H2SO4, HClO have the general formula HNYOM, right? Where Y is non-metallic and NMM are integers. Atom Y is always bonded to one or more hydroxyl groups, OH groups, and can be bonded in addition to one or more oxygen atoms, right?
Yeah.
The
Yeah.
common
Yeah.
structures are given, 3-4 structures are given. So because the dissociation of an oxo acid requires breaking an OH bond, right?
Yeah.
OH bond. So ultimately on all these acids, the H plus that comes out is breaking the OH bond. See?
OH bond.
In all 4 structures, OH bond has to break, right?
Yeah.
So any factor that weakens the OH bond, right, or increases its polarity, right,
Yeah.
will lead to an increase in acidity.
In acidity. Yeah.
Right? So if you can increase the polarity of that OH bond, then your acidity will increase. So clearly now carbon, if you place carbon there in carbonic acid and replace it with nitrogen, right? Then nitrogen is much more electronegative, right?
Yeah,
Yeah, yeah,
So the effective value of electronegativity will be much higher this side if it is N, right? Instead of C, right?
yeah,
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 N will pull the electron cloud towards itself and much more than C will do that, right?
yeah,
yes.
So the bond polarity of OH will increase there, right? So HNO3 is much more strong
much
than
more strong.
H2CO3,
Yeah,
right?
yeah,
Similarly, sulfuric acid is more than carbonic acid, right?
yeah,
Yeah,
Sulfur
yeah,
is also, sulfur is not ideal, but it is still in the sixth group, right?
yeah,
Sulfur will be more electronegative, right? So it will
yeah,
definitely more than carbon. So that will also increase the polarity of OH bond, right?
yeah, yeah,
And if you have a Cl, then it will be much more strong, right?
much stronger.
Hmm.
Yeah, makes,
Much strong electronegativity, right?
yeah,
So,
yeah,
so as you go towards the right hand side again in the period, right? Then your bond polarity is increasing and acid strength is increasing,
yeah,
yeah,
right? So now, okay. So then the next few points are for oxo acids that contain same number of OH groups and same number of O atoms, right? The acid
yeah,
strength increases as electronegativity of Y increases, right? Which is fairly understandable. Since HOI, HOVR, HOCl have same everything, then then acid strength will increase depending on which is pulling the electrons more from H, right?
yeah,
yeah,
HCl is pulling the electrons more towards itself, right?
yeah, yeah,
HOCl, right?
yeah,
There the polarity is more, so acid strength is high. Now, as the halogen becomes more electronegative, an increasing amount of electron density shifts from the OH bond towards the halogen, thus weakening the OH bond and strength increasing its polarity, right?
yeah, yeah.
hmm.
The second case is when the number of O atoms is changing, right? So for
Okay.
example, HClO, HClO2, HClO3, and
Zero
HClO4,
four.
right? Obviously, O is a highly electronegative atom. So if you add more O atoms, the polarity is further increasing, right?
Yeah,
Yeah,
So the group Cl, it's alone Cl is going to pull electrons by a certain degree, but ClO will pull more, and ClO2 will pull more, and ClO3 will pull more, right?
yeah, yeah,
yeah, correct.
Right. So
yeah,
OH polarity is highest in HClO4,
Yeah,
right?
hmm.
So
Yeah, yeah,
therefore, the strongest acid will be the perchloric acid, HClO4, right?
hmm.
So the dissociation constants have also been mentioned. So you start with something 10 power minus 8, and then it is 10 power minus 2, and then almost 1, and then very large.
yeah,
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 So you can see the trend in oxidation number also. So oxidation number of chlorine is +1, +3, +5, +7 here, right?
yeah,
Because
hmm.
oxygen will always have -2 in these types of settings. Oxygen will always have oxidation number -2, and you have to adjust others accordingly.
yeah,
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 Right? So that is the situation here. So as the number of O atoms increases, acidity increases. Now, next thing that he's talking about is in the next paragraph. Another factor that affects the acid strength of oxo acids is the relative stability of the corresponding oxo anion, right? So,
yeah,
so once an acid dissociates, the anion, if you can stabilize the anion, right? If you can make the anion that is formed more stable, then that will increase the acidity.
hmm.
Why? Because product is more stable, then it is likely that the reaction will happen.
Yeah, yeah,
Because product is more stable means it has lower energy, right?
yeah,
So
yeah,
the reaction will proceed further because the enthalpy gap, it's more exothermic, no, this gap,
yes, yeah, yeah,
right?
yeah,
yeah,
Something, the product side is having lower energy, then it is better because more exothermic gap will happen, right?
hmm.
So he's saying the ClOm minus anion becomes more stable as the number of O atoms increases in the series,
Hmm.
because a larger number of electronegative O atoms can better accommodate the anion's negative charge.
Yeah. Yeah.
So if there are more than, say there are ClO4 minus, right? And there are 4 O atoms over which the charge can be distributed, right?
Yeah.
The ClO4 minus will have 4 O atoms to distribute its negative charge over. However, ClO minus will have only one oxygen which has to share all the negative charge, right?
Yeah. Yeah.
So stability of the oxo anion, if it increases, right, then the acidity.
Yeah. Yeah.
So as the stability of the anion increases, the corresponding acid has a greater tendency to dissociate. The increase in acid strength with increasing number of O atoms is further illustrated by the oxo acids of sulfur. So H2SO4 is stronger acid than H2SO3
Yeah. Yeah.
because you have SO4 to SO4 minus. No? So 4 O's can
4 O's, yeah.
accommodate the
Yeah.
negative charge, right?
Yeah.
Yeah.
And the
Yeah.
other one HSO3 minus, right? So 3 O's
Yeah.
only,
Yeah.
right? So that is the reason. Then we come to Lewis acids and bases. So Lewis acids and bases is the final definition. So here you are talking about a new definition of acids and bases, which extends the idea even further, not just a proton donor and a proton acceptor, but electron pair acceptor and electron pair donor, right?
Yeah.
So if you think about a proton, the way it reacts is it accepts an electron pair from something, right?
Yeah.
Yeah. Yeah.
Proton, when it attaches to something, right, it has to take 2 electrons to attach to something, right? So a proton, a bare proton H plus is an electron pair acceptor, right?
Yeah. Yeah.
And a proton acceptor, right, is an electron pair donor, right?
Yeah. Yeah.
Are you understanding what I'm saying?
Yeah.
Yeah.
So something that gives off a proton, right?
Yeah.
H plus and Cl minus, something that is giving off a proton, right?
Hmm.
Is this thing can be thought of as this. Okay, so it has given off H plus, and this H plus is an electron pair acceptor
Yeah.
in a future reaction. This H plus is an electron pair acceptor. On the other hand, OH minus, right? OH minus has extra electron pairs, right? So it will be an electron pair donor,
Yeah.
right?
Hmm.
So just understand the relationship between Bronsted-Lowry acids and bases with Lewis bases and acids by thinking that the standard Bronsted-Lowry acid will be an acid because this is there.
Yeah.
H
Yeah.
plus is there in that, and H plus will be released because of it, which is an electron pair acceptor. So this is a Lewis acid definition. This is a Lewis acid if it is an electron pair acceptor, and this is a electron pair donor. OH minus is an electron pair donor because it has extra pair which can be donated to something and form a bond, right?
Yeah.
So this is a Lewis base. Okay, this is a Lewis base. So the real idea here is thinking of compounds like this: BH3. BH3 compound is boron hydride, and this compound has only 6 electrons in its valence shell. If you draw the structure, you are having only 6 electrons, so you can only do this, right? So now this compound clearly is missing an octet, right? So it will react with anything that can donate an electron pair to it, right?
Yeah.
It will be an electron pair acceptor, right?
Yeah.
It will want to be an electron pair acceptor. So who can donate an electron pair to it? An OH minus can donate it, right?
Yeah.
OH minus can donate it, no? One electron pair to it, right? So definitely it will react with OH minus, right?
Hmm.
So OH minus is an acid, it's a base. So this is a Lewis acid. This is a Lewis acid.
Yeah.
And OH minus will be the Lewis base. Okay.
Hmm. Yeah.
So let's see the examples that he's talking about. So NH3, for example, ammonia, right? Ammonia has a lone pair of electrons on the nitrogen, right?
Yeah.
And that lone pair is being donated to the proton to form NH4 plus.
Hmm.
So lone pair, electron pair donor will be a base. An electron pair acceptor will be an acid. So H plus is the acid, NH3 is a base.
Yeah.
Yeah.
Okay.
Yeah.
So now he's saying, he's defined it, then he says, because all proton acceptors have an unshared pair of electrons, right? All
Yeah.
proton acceptors, anything that accepts a proton obviously has electrons that it can give to the proton. No?
Hmm.
All proton acceptors have an unshared pair of electrons, and all electron pair donors can accept a proton, right? The Lewis and the
Yeah.
Bronsted-Lowry definition
Yeah.
of a base are simply different ways of looking at the same thing.
Hmm.
Yeah.
Something that Lewis Bronsted-Lowry definition was a proton acceptor, right? H plus,
Yeah.
something that takes an H plus, right?
Yeah.
Right. So, and Lewis one is electron pair donor, right?
Yeah. Yeah.
So that is the same thing you're looking at in different person's perspective, right?
Yeah.
Right. So similarly, all Lewis bases are Bronsted-Lowry bases, and all Bronsted-Lowry bases are Lewis bases. The Lewis definition of an acid, however, is considerably more general than the Bronsted-Lowry definition, right? Lewis
Yeah.
acids include not only H plus, but also other cations and neutral molecules having vacant valence orbitals that can accept a share in a pair of electrons donated by a Lewis base. So common examples are Al3 plus. So we saw earlier Al3 plus, right?
Yeah.
Was behaving like an acid, right? But
Yeah.
if you thought of it like a Bronsted-Lowry situation, then how will Al3 plus behave like an acid, right?
Yeah.
It doesn't have H, right?
Hmm.
But Al3 plus, what it has is a lack of electrons.
Yeah.
So
Yeah.
what it will do is it will accept electrons from whatever source it can get, right? So it is an
Hmm.
electron pair acceptor, right?
Yeah.
That is called a Lewis acid. So now you see hydration. We explained it earlier by thinking that it is getting hydrated and the hydrated thing is losing protons, right?
Yeah.
You understand? So, but the hydration process itself is an acid-base reaction.
Yeah.
Hmm.
Al3 plus is taking the 2 electrons on the oxygen atom of water and becoming AlH2O6 3 plus, right? See,
Yeah.
it is taking the electron. So it is an electron pair acceptor. So Lewis base, Lewis acid, and the other one is an electron pair donor. Water is acting like a Lewis base.
Hmm. Yeah.
Hydration reaction itself is an acid-base reaction. You understand?
Yeah.
Hmm.
So similarly, more examples he has given. BF3 molecule he has given. BF3 we just now discussed.
Yeah.
We discussed for BH3. It is the same thing. BF3 will also be missing an octet.
Octet. Yeah.
So it wants to accept electron pairs from anyone. So BF3 will be acidic.
Yeah.
And BF3 can react with NH3, which is a Lewis base, and becomes this acid-base adduct. Similarly, like once you draw the structure, no, it will be clear to you what that compound will do, what the compound wants to do, right? So if it is an electron pair acceptor, it's a Lewis acid, otherwise it's a Lewis base, right? And the strength of the Lewis acid or base depends on the strength of the tendency to accept electron pairs or donate electron pairs. So if after accepting an electron pair, the formed compound is very stable, right? Then it has a high tendency to form that compound, right?
Yeah.
It will be a stronger Lewis acid.
Yeah.
So that is what it is. This is basic conceptual stuff. We will revisit this whole acid bases and strength of acids and bases in the future. So we'll see that. Yeah, and there will be more instances where we learn different trends and different properties for acids and bases, especially in organic. So
Okay.
anyway, we'll come back to it. Okay, chapter 15, a little bit is still left. We have to do the titration curves part, right?
Yeah.
In
Yeah.
Alan, it is done, titration. No?
No, we haven't done titration.
KSP and all
No.
has been a solubility product, no?
No, we were doing the, what is it?
In right now, what is going on in Alan?
We're still doing the pH and class.
Okay. So see, 15.4 we have already done till 15.4.
Yeah.
15.4 is the
Yeah, we have done the-
Henderson-Hasselbalch equation.
Right.
That is the buffer solution stuff.
Yeah.
Okay. So
Yeah.
that part you should revise. 15.1, 2, 3, 4 buffer solution stuff. Then pH titration curves, let's do in the next class. Okay.
Yeah.
From there onwards.
Yeah.
So
Yeah.
actually, let's do an extra class for chemistry also someday. Like this week, the next coming week, we can have 2 classes for chemistry. I want to finish this in 1 or 2 weeks so that we can start organic.
Yeah. Yeah.
So just try the questions of chapter 14. Okay.
Yeah. Yeah.
Try the questions of chapter 14 and first 4 sections of chapter 15. Right.
Yeah.
Yeah.
It will probably take us 2 classes to finish everything till 15.15. Okay. So we will start with 15.5. Okay.
Yeah.
So 10 sections are there. So probably 2 classes.
Yeah.
Okay. So we have to do it properly. Till 15 chapter we'll finish and then we'll start the next thing. We'll start organic.
Okay.
Okay. Okay. That's all for now then. I will tomorrow probably will be physics for you. I'll just
Yeah.
message
Yeah.
Rahul.
Yeah.
Or you guys also ask him. Like he will
Yeah.
set a time and all. Okay.
Yeah.
Okay. Sunday will be maths. We'll do maths for some time. Okay. Okay. Bye.
Nice.
Bye, sir.